for Thanks a lot, Ashley, for the introduction and inviting me to Cal Hill, which from the outside kind of looks like an alien megastructure. So I'm honored to give a talk here. So yeah, today I'm gonna step away from the familiar home of the solar system, the small bodies that I work on, Io, Europa, Titan, Triton, many small active bodies, and work on exoplanets, or talk to you guys about exoplanets. Want to go ahead and thank many of my collaborators down here that have contributed to this work in some way. Yeah, so let's see if I got to click. Okay, so some conventions to get started. I'm going to focus primarily on two types of exoplanets and exomoons, namely an exo-Io and a super-Io, just to make that analog clear. And so an exo-Io I define as a volcanic satellite of roughly lunar mass orbiting a gas giant exoplanet whose evaporation sources a neutral or a plasma torus, or a cloud, an extended cloud. And then a super-Io is, I think it was referred to first in Wade Henning's white paper, and it's a volcanic super-Earth-sized exoplanet whose evaporation may also source a similar phenomena. So starting with the origin of these evaporating super-Ios, starting in the long and millions of years to giga-years planetary evolution timescales, we think these rocky planets might evolve from sub-Neptunes who lose their hydrogen-helium envelope, then become some sort of bare core, an astrophysical bare core. And then when that starts disintegrating, we can form a volcanic rocky body that has thermal outgassing from the surface. So sort of sequence of events from there. And so that's a good starting point to talk about planet evolution in general. In Switzerland, I worked with Christoph Mortesini, where we studied planet population synthesis. So let's see, does this work? Yeah. So this plot right here simulates many sub-Neptunes with the hydrogen-helium envelope. And as you can see, the fraction lost as it turns more and more brown and black, it experiences atmospheric escape so that the sub-Neptune loses its envelope and then evolves into a so-called bare core. And that's all the way down here around 1.6, 1.8 Earth radii. And as you can see, these are is a population that's that we would like to compare to Kepler data. On the right-hand side, I just have a series of papers that are coming out regarding these simulations. One is already out by Christoph Mortesini, where he studied this analytically to show that you can actually derive this valley in the Kepler data analytically, just using energy limited escape from the XUV radiation from a star, which we'll talk about. A paper we have in review, just for full disclosure, is fitting the slope of the radius valley by not only XUV driven escape, but also Boy law and hydrodynamic regimes, which is led by a graduate student, Lukas Affolter. And then finally, a paper from the before times in 2019, I think that was my last in-person talk in Geneva, is on the dependency of the evaporation valley on the host star mass. So whether it's an F star, a G star, K star, or an M dwarf, the evaporation valley will change. So right here, you can see maybe a more clear data-driven simulation, where this is the Kepler data, where many people in this room perhaps have contributed to the California-Kepler survey. And so this accounts for the biases in the data, and you can see that we can fit the bare core mass right in between to show how the population of sub-Neptunes are indeed very different than the super-Earths. And the trick of the game, at least in planet evolution, is to try to fit the valley in terms of whether it's too steep or too shallow, and then to try to use physical processes to motivate this slope. And some details are provided here. And so, yeah, this is the so-called last talk I gave before today in person. And here we studied by launching several thousands of simulations to study a population versus host star mass. So here we've simulated half a solar mass all the way to 1.5 solar masses, and we can see that this roughly is in line with the latest results by Eric Pettigura in 2022, which I just saw this morning thanks to Andrew. So yeah, the point here is that the smaller cores can keep their hydrogen helium envelopes as the stellar installation decreases. So we can see a downwards trend this way. And if we focus just on 3 days here, we can see that the bare core increases from about 2.1 all the way to about 2.5, 2.4 Earth radii. And so that's similar to the result from the California-Kepler survey. I mentioned that that's not the full story because we're still exploring the parameter spaces to see what other physical processes can change between star masses, because it probably is not only the stellar flux. This is actually a very simple model using XUV energy limited escape. And I'll talk about some of those other atmospheric escape mechanisms today. So try to review that and say that we can study and use atmospheric escape in 2 ways. The first one being what I just described, that we can study exoplanet transit radii from precision broadband photometry and determine these radii and see how they look in a large population. So starting with the oldest known escape mechanism from, I think, the 1910s, this is Sir Walter Jean's kinetic model, where essentially this lambda parameter is the infamous Jean's parameter, and this calculates atmospheric escape on a molecule by molecule basis. So it's a kinetic model, not a fluid model, although it is still thermal, because this term right here, dmdt naught, is the outgassing rate. So outgassing, just as a quick overview, is just the gas release of volatiles that are absorbed or trapped in a body. So when studying these bare cores, it's very important to make sure that there is enough atmosphere to escape from. If there's no outgassing, there won't be any atmospheric escape. And so these are just a few of the terms that we use in the solar system to describe these processes. And of course, outgassing might be the origin of Earth's atmosphere itself, and of course, the source of several tenuous atmospheres in the solar system, such as Ganymede's atmosphere, Europa's atmosphere, Triton's atmosphere. Moving on to upper atmosphere and plasma-driven escape, which is a little more relevant at close and exoplanet systems that really drive this evaporation. Just showing a sort of condition here, was what I was saying earlier, that the outgassing condition the escape needs to be greater than the outgassing rate, or else you don't have anything to escape from. And sometimes, I'll go back here. Yeah, sometimes atmospheric escape can be complicated, but I tried to make it in the simplest possible way, that it's simply the ratio between the energy input into the atmosphere over the binding energy per molecule. So essentially, one needs to assess and add up all the heating processes that can occur that can then drive it off from the gravitational well. So there's 2 possibilities. You can either have Q plasma or Q XUV, the plasma heating or the XUV heating, which you can calculate just by taking the cross-section, the absorption cross-section on the day side atmosphere, especially if it's tidally locked. The night side won't experience that. And then, of course, the XUV flux, which can be done by, if you have knowledge of the X-ray luminosity or the EUV luminosity, you can ascertain the XUV flux. Now, the plasma heating is much more subtle and much less studied at exoplanets. Searching the literature, I think it's possible that equation 14 here is one of the first analytical expressions to describe this, in the sense that the P right here refers to the plasma pressure, And so this can be calculated by adding up the magnetic pressure from the star if the planet is super close in a subalfvénic regime, or the ram pressure from the stellar wind, which can smack the planet and cause momentum transfer that causes a cascade of collisions, and then that rebounds out to space, out of the gravitational well, in a phenomenon known as atmospheric sputtering. So for instance, at Io, that's the known escape mechanism. It's not hydrodynamic, and it's also not Jeans escape. And so the trick or the tough part is Rx, which is the exobase altitude. And so doing this for Io, even this is not well known at our own moon. And oops, one more time, it's at 200 kilometers if you backtrack the observed escape rate and derive Rx, which is consistent within a factor of 2 of simulations. And I would advise maybe checking out Bob Johnson's book, 1990, which has charged particle interactions, which is written generally enough that it can be useful to exoplanets and escape. Yes?
Can you explain it again, the Rx term? Why is it so uncertain?
Right. Rx is an exobase altitude, so at which an atmosphere gets collisionless and transitions to the exosphere. And it's so unknown because we don't have enough data to properly get a TP profile of Io and its exosphere especially. So even in situ detectors would need to have an enormous sensitivity that still hasn't been done. Yeah. So moving on to the second method, which is more of the characteristic of the title, evaporative transmission spectroscopy. This is the new idea from Gebek and Oza, where we just take a absorbing species in high resolution with a resonant wavelength, and then try to estimate the evaporative column density due to atmospheric escape. So that can be observed. And a list of the critical and important parameters are listed right there, in case. And yeah, so the tool I use to do this, mostly stay analytical and do many numerical simulations afterwards. But first, it's just a simple formula where we want to calculate the heating inside the body. These are benchmarked to Io and Europa, that's why they're shown there. And then estimate the mass loss to the surface, and then simulate that evaporative column density. I guess, yeah. So now I'd like to explore the parameter space for these two bodies. So since the first step was to calculate the heating and the heating of the solid body itself, gravitational tides are very important, as are thermal tides. So the first instance here, or the first case, this is a super Io, 55 Cancri E. And as you can see, it's twice the size of the Earth and about 8.6 the mass. And it has an extreme day-night gradient, so that thermal considerations are quite important in terms of a day-night wind or a torque that can actually put the planet into an asynchronous state. And by the way, the host star is a K0, I think 4 star. And I think the stellar age here, I don't believe anymore as 10 gigayears, but I think it's, I use Eric Mamajek's value, which is 7 to 8 gigayears. But that is uncertain, as many people know. And then the ExoIO, putative ExoIO here, this is a hot Saturn system, so a density half the size of Saturn. So I continue to think that's anomalous. And next is the heating rate. So the heating rate, just for reference, 10 to the 21 watts, 10 to the 18 watts. Io's total heating rate is 10 to the 14 watts. So we're working in a regime that's 6 to 7 orders of magnitude higher than Io itself. And here I've just illustrated the Roche radius of the gas giant, at which if there was a body, and if it ever entered inside this Roche radius, it would be disintegrated immediately. So yes, the stellar tide would disintegrate it and cause runaway disintegration. And here are a few of the expressions that I use to calculate the tidal energy that's input into the body by the stellar tide. Some of them are famous and well-known, such as Peel 1979, which is the analytical expression that was used to predict Io's volcanism before Voyager 1's encounter, where the plume was actually observed. And this is a 3-body tidal heating rate of a moon calculated by Cassidy et al. 2009. And I summarized it in our paper. Right, so then one can calculate the outgassing rate, and these are maxima. So of course at noon, and perhaps if it goes to the night side, it will be much less, but just to show the extremities, the end members, these are enormous rates, which just demonstrate that atmospheric escape will occur and will have plenty to be fueled from. So the actual upper atmospheric escape rates, or energy limited escape rates, are on the order of 1 billion grams a second. So this is quite considerable and approaches like losing half a lunar mass per gigayear. So the real question that we studied was whether these, at least the exo-Ios, survive, and then does this drive volcanism? Does it drive extreme volcanism? What does it do on the surface? Because the rates suggest an atmosphere that's going into free space, but then also falling back onto the surface, since most of the source rate actually, since the source rate is so much larger than the escape rate, most of the material falls back down, creating an intriguing scenario for a super Earth planet. Okay, and I often get the question of how can you have volcanism on a world that might be completely molten, which is a very fair question. Of course, if it's just liquefied, we don't have volcanism, but I did want to show these curves of sublimation rates that now I have units of tons a second, so divide by 1 million if you want to go back to grams, or sorry, multiply by 1 million. Different compositions will, of course, yield different sublimation rates and different outgassing rates. So what I wanted to outline here with an idea for time in the scenario that the planets or the moons are asynchronous, and they're not, well, the moon will be tidally locked, but still experiences a diurnal variation. But a tidally locked planet could have an asynchronicity, which could have time evolution. And so if you do have temporal evolution, I just mapped this from dawn to noon with a reasonable range of temperatures observed by Spitzer for 55 Cancri, and those are brightness temperatures, so it could be much higher. Can actually see that the melting point occurs later. So at dawn, you have considerable rock to erode. And I think that's just something I'm learning, that when you start trying to model the geophysical evolution with atmospheric evolution, the composition will affect these results in some way. And then, so backwards, maybe one can infer the composition from a result in spectroscopy. Yeah.
There's a question. Luke, do you want to ask it?
Yeah, sure.
Sure, yeah, if the audio is working. So I think that this was just covered and I didn't quite catch it. So in what scenarios does the outgassed material remain bound to the planet versus become unbound but form a plasma torus, just like in the Io case?
Right. The rates I showed showed that sublimation on these worlds can strongly overwhelm the escape, so that there's significant material coming back, but the material that's escaping is still going to space and fueling potential Taurus. So were you also asking what scenarios, meaning what mechanisms, or did that sort of answer your question? Sublimation of rock versus atmospheric?
I guess I think so. Well, well, for the case of the close and rocky exoplanet rather than the exomoon case, I think like the solar wind is also a factor, because that can affect whether or not the Taurus is going to remain stable once the plasma has escaped from the planet, right? I don't know that much about this. I'm just kind of speculating.
Oh, yes, I see what you mean. Yeah, well, we're actually on that topic right now. So just going from here, let's see if I can go back. Oh, yes, hold on. Right, so going here, this is the first time I drew a toroidal geometry here to highlight how they would be very different. So the two systems, one is much closer in, like almost 3.5 stellar radii. So it's, I think, in a subalfanic regime, so that it would have significant interaction with the star, and so the toroidal geometry would be perturbed. If one is farther out, it's possible that a plasma torus could exist, but then if the magnetic field of the exoplanet is not known, then one may have difficulty modeling the precise geometry, but we just use a torus for simplicity. And the geometry of the torus, I think, is remains unknown, but it's the densities that I think are interesting. So yeah.
Got it. Thank you.
Thank you. That's a good question. Right. So, and then this schematic diagram is just to illustrate the various processes that could occur. That besides a torus, one can also have an ejected cloud. And these clouds here, and even this, are to illustrate that if one is going in to do gas absorption spectroscopy, which I'm about to show in a few slides, for instance, for sodium, the sodium must be neutral, and in order to give the sodium D line absorption. So the ionization timescale that I've listed down here is critical, in the sense that this close into the star, the sodium would be ionized in a minute, and then at even 8 stellar radii away, it's ionized in 4 minutes. And so there should be significant ions if there's significant venting from these bodies. And so that's one of the major, I guess, that has some major implications, which I'll talk about. Right, and then to actually convert from mass loss to a column density works as a minimum from ISM physics, that if we can constrain the equivalent width of a line, we can know the column density. And then if we want to do a forward model to predict the column density, and with the only source of the column above the atmosphere is what's happening below the atmosphere, then the evaporation rate, the neutral evaporation rate, and the neutral column density is just linearly scaled with the ionization timescale. And then so that gets the total number of neutral atoms in our line of sight divided by the cross section of the star. And so that way we have every line of sight integrating and calculating the average column density that's seen during an exoplanet transit. And I guess that's the basis of that column. I'm gonna skip through this. Okay, so now we can go in and focus on exomoons a little more. It's actually a nice Caltech result. Peter Goldreich in 1977 showed that the tidal Q of Jupiter is actually anomalous, and that the theoretical tidal Q, which is just inversely proportional to the tidal dissipation, if one wants a qualitative or a quantitative analogy, should actually be around 10 to the 12th. I think it was originally in 77, 10 to the 13, went down order of magnitude. Yanxin Wu did some improvements to the tide model. And so in our first paper in 2019, I just modeled all the so-called candidates for exomoon detection and found that they're all in a safe regime below this tidal Q. So that, and why tidal Q is important is that if it's lower, if it's higher than this, they would immediately get scattered. And non-detections at certain planets at the time suggest that perhaps the true tidal Q of hot Jupiter's is a little bit lower, but not quite Jupiter's. And Jupiter's tidal Q would be down here. I'm going to say that last part again, because I think it might have been slightly confusing. The famous paper, Barnes and O'Brien, 2002, claimed that no close-in exomoons can exist on the basis of tidal Q. And that tidal Q parameter was chosen as 10 to the 6 right here. And so in that case, all of these planets would be not stable due to tides from the stellar tide. But the recent calculations of Cassidy et al. Showed that those tides actually go into a putative moon. So if there is a moon, it would not fall into the planet if it's in a stable regime inside the Hill sphere. And actually it can't be just inside the Hill sphere, but very close to the planet. So this plot I don't think does it justice, but I'll try to show some other stuff. And just to show how strong the stellar tide is, of course, should be taken into consideration. All these exo candidates here are very, very close and have a very high tidal dissipation rate. Just to show Jupiter's tide in the same axis on the left, Io is here. Europa is interestingly higher, which is why I think it's oceans, but then it's gone. The tides have gone into the ocean, and so it may have cryovolcanism, may not. And then Ganymede down here. So just to show how extreme these tides can be and volcanism could be expected. And so perhaps save this slide for the end, but just to connect the dots. The point of evaporative transmission spectroscopy is so that we can launch a spectral survey and to search for these exomoons around close-in gas giant systems. And they should, of course, be rare because I think it's very tough to keep the moon while you're migrating in, because as hot Jupiters, we think they migrated in. We don't know whether from the beyond the ice line or not. And so for now, in the literature, many of these volatiles, especially metals, iron, titanium, it's all, most of them have been interpreted as solar abundance from the formation of the gas giant itself. And so from a solar system perspective, one would think there's many moons and we should search for them specifically in the volatiles that we see in the solar system, such as sodium, which is surprisingly bright. And so for that, we've been awarded many hours of telescope time. And even if you get many hours, of course, the night can be cloudy or the instrument can break. So it's not so much there. So we're still working on it. But some shout outs to Caltech here that we have high-res tech data to search for these exo-IOs. And we're in the process of analyzing that right now. And so I'd like to show some results, preliminary results so far, and yeah, maybe motivate the search a little more. So motivating the search is that at Jupiter, if you look at Jupiter from the Earth, or maybe from another star system is a better analogy, you would see a giant sodium cloud extending to 1,000 Jupiter radii. And this is fueled as you zoom in to 70 and then 15, fueled by this tiny little moon, Io. And this is an image taken by Nick Schneider in the 90s, so it's vintage. And so this top panel here is neutral sodium, and the bottom is ionized sulfur, which is ejected from the sulfur dioxide. And sodium, the origin of that sodium is actually sodium chloride, so table salt, ejected out of the volcanoes. Much is unknown of where and what ratios the sodium chloride is, but the detection paper reported 0.3% of the atmosphere, so it's trace. What is interesting in this video, an image, is Io is that bright blob. This bright blob on the left is Europa trying to take the limelight. And what's super interesting is there's still sodium right here on the other side of Jupiter, where there is no moon or there is no Io. And this is because of the plasma torus. So this plasma torus you can see gyrating, but the plasma torus has ionized sodium chloride embedded in it, which undergoes a series of reactions that can create fast sodium. And so that charge exchange sodium shoots off at 100 kilometers a second and actually populates this giant 1000 RJ sodium rectangular cloud. And so in that case, this would imply that at an exoplanet system, if we wanted to say sodium is from an exomoon, it should exhibit significant variability, or we would hope so. And one more idea, although this might be slightly less certain because it could be from comets. Jupiter's atmosphere was observed in transmission, in that same technique we use to identify volatiles at exoplanet atmospheres. And so this was, sorry I didn't cite it, but an observation by Montañez Rodriguez at the Canary Islands and Enrique Pale's group. And so it's a very, very clever observation where they monitored Ganymede and then used Ganymede, which has no sodium, to subtract out the solar Fraunhofer lines. And so in that way, one can obtain a transmission spectrum of Jupiter. You can see the familiar sodium doublet here. And in our paper, we showed that this was very plausibly from Io. Although one could have bombardment from comets over time, it seems obvious with Io just next door. Okay.
Question on that.
Yes, yes.
Is the velocity width of that appropriate for the velocities you're talking about?
Of this line?
Yeah.
Yeah. I can't remember the precise velocity we saw, but it looks about 10 kilometers a second or so. At least I think that's what the model we used fit it to.
Oh, so you mentioned the bound of like, so if you look at like the whole distribution of velocities in that sort of halo, right? You said like over 100 kilometers.
Oh, okay. Yes.
Is that, or is that not thinking wrong?
Yeah. So this that's a great question. This doublet is just the sounding of Jupiter's atmosphere. So actually, this should represent sodium that's been accreted onto Jupiter. So much, we would expect lower velocities, or maybe even static, actually. But yeah, the sodium doublet, the observations of this in spectroscopy reveal many interesting features, or you can see the 100 and the 10 kilometers a second component. Should have shown that next time. Okay, so to model all this, we've developed some software. Andrea Gevic, who's now at the University of Ghent in Belgium. And so this is just to bring the idea that we can observe exospheres of exoplanets. So even if they're not collisionless, there can be a tenuous volume of volatiles that can be observed in transmission. And so that's part A, but part B is that these atmospheres, even if we think that they're from the gas giant itself, need not be hydrostatic. Earth's atmosphere up to, I guess, Mount Everest is a nice scale height, but above we have inversion layers, etc., and also atmospheric escape. If we look at Mars, completely different, many, Venus. So we created a tool where the user can choose the number density input, whether you want maybe a hydrodynamic structure of an escaping atmosphere, maybe you want to test a moon, or you want to test a torus or a ring around the planet. And so that's the key idea. I made this plot just this morning. So sorry I didn't label all the planets here. What I'm showing here is some results from Lene Quick et al., where their team and Amy Barr, they calculated the total heat dissipation of exoplanets. So this is 55 Cancri E. I know that one by heart. This horizontal line is Io, and let's just say these are all Kepler planets. So I can provide the list. It's table 4 in Quick et al. So this is just to show that the evaporation rates, and in particular the sulfur dioxide evaporation rate, if you choose that as the volcanic volatile of interest, can actually be calculated. And if you use evaporative transmission spectroscopy, you get tenuous column densities that may be observed by JWST or other infrared observatories. Just so in case if there are no exomoons, well, you can still find extrasolar volcanism, hopefully. And yes, so for the exomoons, I made this neat little plot last night. And so, sorry if it's a little clunky, but the semi-major axis in solar radii is here. The semi-major axis in Jovian radii for the moon is on this XY Cartesian grid. And then the temperature is on the z-axis with the evaporation rate provided here. And so immediately, for instance, WASP-52, very close into its star and pretty much hugging the Jupiter according to our dynamical calculations. And all of these planets are very, very close, not depicted as Io, which would be way out here at about 6 Jovian radii. So it's not, so if there are exomoons, they would be very close to their star, their host planet. And the evaporative column density one can calculate is easily observable, whereas this SO2 column density is a little tougher. Sodium is so bright that this has already been seen, and so it's a question of interpretation. So nevertheless, here's some data. So this is from our figure 5 in our AppJ paper, and observations of WASP-49. So what you're seeing is binned observations averaged over 3 nights of sodium D2 right here, and then sodium D1. So what you're seeing is neutral sodium signature that creates this line. And so if we test a hydrostatic model, we actually get this profile. So it looks like the line depth does not reach as far. You can arbitrarily increase the heat of the atmosphere and get it to work, but we didn't. But you can get it to work on the depth, but not the broadening. And then if we actually use a realistic escaping atmosphere and even pump up the sodium 100 times the solar abundance, it works a little less. And again, the line is very narrow because the speeds are, not as high, although winds can be used. So at the time, we had an ExoIO model, which we've significantly improved since then. And we got it to work essentially on the first try, because what we used here is the profile from Io itself to drop off the sodium, where a hydrostatic profile would drop exponentially. A sputtered profile from the mechanism we had discussed earlier would be a little more gradual. And so that was that. So calculating the mass loss rates now in kilograms a second, we can see that since the equivalent width of these lines does give a minimum abundance, at present it seems that the planet can't supply enough sodium, and so a putated moon seems to be reasonable. Yes.
This is a question.
Oh yeah.
Jess.
Hi. Thanks. In those models, so sorry, I think I misunderstood. Is the sodium infalling from the moon into the planetary atmosphere? Is that what these models?
No, actually, we assume that the moon is somewhere in around the planet, but not necessarily infalling. It's just escaping and then either leaving the planet's hill sphere, or it's yeah, just involved in the hill sphere in a
Oh.
toroidal way.
And so these data, this transmission spectrum, is it the immediately out of transit spectra compared to the in transit spectra, right? So it's just so it is all the stuff that's very yeah, close to the, it would have to be very close to the planet, right? Okay, gotcha. Sorry. Thank you.
Right. No, that's a really good question, and I think it's a great segue to what I'm about to show, in the idea that where is this moon? So we can place this moon. We have no idea where the moon is actually. So we just try to model it by creating this visualization software. And once again, looking for sodium variability. I'm going to skip that for now. Yeah, go to this. So if this works. Oh, it works. Okay, so this is placing the moon right in front of the planet as it transits. So hopefully here you can get a visualization of the sodium cloud around only the moon, not from the planet, and then see what it looks like in real time once the movie loads. Let's try. Playing. Play. Okay. I guess it was a too high resolution. Okay, so here you are waiting for the planet to transit, which is very well known, and then suddenly there is a cloud of sodium before the planet actually transits mid-center. And so that's what we call, this is a phase angle at 0.25, so it's leading the moon. It would be at planetary dawn. So let's see, what does it look like if it's at noon? So behind the planet, here, as it loads, it's actually being occulted behind the planet. And so if you look at the column density here, it's much, much smaller because it's the moon is so tiny compared to the gas giant, so that the sodium cloud, even though it is indeed extended, would only have its peripheries viewed during transit. And so that could be one explanation for non-detections of sodium from night to night. If you see sodium one night and then you don't see it the next night, well, the planet's always there and atmospheric escape is always happening. Right, so I think these are about the same. Yeah, I've already done that. Yeah, so just to conclude, and I know I talked about two major topics, exoplanets and exomoons, but in conclusion, I would like to bring us all towards this idea of geophysical characterization of super Earth exoplanets. We know that from real data from Kepler that we can potentially start to characterize these worlds with small radii, super Earth-like radii, even Earth mass radii near the stars. And because of that erosion process, we can infer some geophysics because of transmission spectra that can reveal elements such as iron, nickel, titanium. We can also geophysically characterize. And I would say that volcanism coupled with atmospheric escape could be a prerequisite for close-in exoplanets. And yeah, I think, let's see, beyond the realm of spectra, no, I'd say, let's get through that. Just wanted to advertise that we do have a research topic in Frontiers to summarize and have a small little booklet for exomoons. Anyone who's working on the topic, look out for that. And here's some tools. And with that, I'll take questions. Thank you.
Thank you. All right. Does anyone online or have questions? Jess, do you have another one?
I do. Thank you. That was, never mind. Yeah, these are super interesting ideas. I wonder if there's any other way to observationally differentiate between this and just straight up sodium in the planetary atmosphere? You mentioned the variability, but is there any, like, this, can you see the shape of these clouds in the light curve and differentiate it between that and escape from the planet itself?
Yeah, extracting, right now we're currently in the process of taking our spectra and then cutting it up night to night and then looking at the light curves. So that's why I so far didn't compare the video to the data, because we're still in the process of looking at that. And so that's one way. Another diagnostic, if I have it listed, yeah, that was earlier, actually. I did want to show this, actually. So these are two other famous exoplanets, WASP-121 and WASP-76. And so here it shows another diagnostic. So not exomoon exoplanet exactly, but it's to differentiate between an optically thin medium and an optically thick medium. So it turns out the oscillator strengths of potassium and sodium, these D lines, if it's about 1, as is WASP-76, it's an optically thick medium. Whereas if it's an optically thin medium, the ratio of the oscillator strengths will actually be the ratio of the absorption lines, the absorption line strengths. And so, at least for this observation, this is Hoymakers et al. 2020 ANA. Here we can see that there's a clear D2 to D1 ratio that indicates an optically thin medium, which is more characteristic of an extended cloud sourced by a third body versus, but it could also be a tenuous wind. So it's not the catch-all diagnostic, but it definitely helps. Yeah, you have another question?
Thanks.
JD, did you have a question or?
Yeah, I just realized I wasn't sure if it was actually a good question, but have you thought about, is that sodium signature something we could detect around directly image planets or something like that? Or is it something you have considered? There's probably many reasons why it wouldn't work, but just, yeah.
Yeah, no, that's a good question. Actually, someone asked me that this morning in one of my meetings, so I think that's a great question. And the idea with that, so for example, these new space-based telescopes such as LUVOIR, HABEX, or Roman, these telescopes will, if you take the HR 8799 system, for instance, these are supermassive Jupiters, so you might expect supermassive exomoons. And especially if they're forming, you would have these moons. And so monitoring them in sodium and doing a continuous monitoring of the D line, and then knowing how to subtract, I think it's an A star, right? Subtracting the A star sodium lines, then one can see variations. But I think that would be tough and would, I think it just requires some thinking about, actually. It seems like a one indicative method, because sodium is that heavy, it's still a heavy metal in terms of 23 AMU versus hydrogen helium that we've mostly been working with. So even though it can be from formation or solar abundance, seeing it maybe perhaps in very strong variations could indicate something is going on geophysically. So I'd say that's a good idea.
Cool. I have a question. So you showed these models at high resolution, and have you thought about how they would look at low resolution, or is it really all the differences concentrated in the core?
Yeah, I know this planet off the top of my head. Maybe I'll just, if I can show this paper real quick. At low resolution, so, oh no, we don't want that. That's like an EPUB. Hold on. Let's see, FJ. I just wanted to show this table from our paper. Okay, it's already there. So,
Oh, you might have to copy it or like change screens.
oh, whoops. Let's see. So I shall share the screen again and share this. Yes. Okay, so this is from our 2019 APJ paper. And a lot of these observations are at low resolution because this was just at the edge of the high resolution wave. Espresso was definitely not online. So these are all just predictions. Some of them were predictions, but hold on, let's see. Go down. There's this particular exoplanet here, WASP 96. And I think there was a Nature paper about this from the UK group. So this was the only planet in the sample that just didn't work. That they were, because of low resolution observations with VLT force 2, they saw pressure broadening. And so perhaps low resolution observations can help determine how optically thick it is and whether it's in an extremely high pressure environment. So at the time, and right now, I'm not sure if I believe the error bars I put here, but at the time, it was too thick and was not able to be supplied by an Io mass exomoon. And of course, we just assume that it's an Io mass. It could be larger, it could be smaller. So, but to answer your question, low resolution, I think, can help with the pressure and those kind of things.
Right, and I guess you would also still see the variability.
Yeah.
Cool.
Yep. I think you'd see variability.
Cool. Jess?
Me again, sorry.
Go for it.
Do you expect a different ratio between, if you could do both sodium and potassium for the same system, could you expect to see a different, sorry, I'm still stuck on this, how to differentiate between planets and moons. Could you see a difference in the expected ratios for the different elements than what you might expect from just a planet alone without an exomoon?
Yeah, absolutely. And that's table 1 of our paper. So
sorry.
no, you guys are just asking really good questions. So just the history of this table or sodium and potassium is actually in my opinion, one of the most powerful diagnostics, because in our own solar system, to determine the origin of sodium at Europa, it was determined that it's not from Io. I think when actually Mike Brown, just next door, he observed and discovered sodium and potassium at Europa, and there was considerable debate whether that sodium or potassium is from Europa or it's from Io, which has all these clouds and it comes and could hit Europa. But taking the sodium to potassium ratio and systematically comparing it reveals that it's even higher than solar abundance. And I don't know if I put it here for Earth. I used the mesospheric value, but that paper, the original paper, has Earth's oceans actually. And it says the sodium to potassium at Earth's oceans is similar to Europa. And so that was the sort of diagnostic, I think, at the time. But I think maybe other people know more of the history. I was 12. But yeah.
Cool. All right, well, we're getting close to the top of the hour and we've had a lot of great questions. So yeah, maybe we'll thank Oza again. And yeah, have a good day, everyone, and see you next time.
See you.